So without further ado, let me introduce our next speaker. So we're very happy to host Professor Daniel Baker today, joining us from Boulder, Colorado in the United States, who, as you can see from the talk, from the title of the talk, will talk to us about societal and economic impacts of space weather. So Dr. Baker is the director of the Laboratory for Atmospheric and Space Physics at University of Colorado, Boulder. He is a distinguished professor of planetary and space physics at Colorado, professor of astrophysical and planetary science, and professor of physics. Dr. Baker received his PhD working under Professor James Van Allen, who some of you may recognize the name, and subsequently worked with Professor Edward Stone at Caltech, the California Institute of Technology. He was group leader for space plasma physics at Los Alamos National Laboratory, and then division chief at NASA's Goddard Space Flight Center. Currently, Dr. Baker holds the Mark Broad-Reach Endowed Chair of Space Sciences. Dr. Baker has been the recipient of many prestigious awards by several institutions and organizations, from which I would highlight the 2015 Shenkuo Medal of the International Association of Geomagnetism and Astronomy for his interdisciplinary work in space and earth sciences. Yesterday, you heard a little bit about plasma physics, and we just started covering space weather at the end of that talk. That is exactly what we're going to hear about now. So without further ado, Professor, the floor is yours. Thank you.
Thank you. Thank you for the kind introduction, and thanks to all of you for being here. It's a pleasure to be able to join you, and I'm eager to learn more about the association that you all are working with. I'm going to talk today, as Pedro said, about the societal and economic impacts of space weather. I thought I might say a little bit more about where I am right now. I'm in Boulder, Colorado. This is a picture of some of our facilities on the East Campus of the University of Colorado. We have about, I guess about 20,000 square meters of laboratory and calibration and accelerator space on the East Campus, and about 700 researchers, individuals who are involved in space research in our institute. And we are involved in a wide variety of science areas, at least space and earth science areas, planetary, atmospheric, solar, stellar kind of research, and space physics. We design and build space hardware. One of our taglines is that we've sent instruments to every planet in the solar system, and even former planets like Pluto. We have a large number of practicing engineers and technicians. We're operating several spacecraft now for NASA and other organizations. And we have strong student involvement throughout. Today I'm going to talk about, I could and would actually be interested in talking about the sort of science branch of this, which is the study of the sun as a star, study of the interaction of the effluence from the sun with the Earth's and the planetary magnetospheres in our solar system. And I also have done a lot of work to do comparative space environment studies and applying that to more astrophysical problems. But today I'm going to really talk about a different branch of this work, which is the more applied side. And this is to understand the effect of the sun on humans in space, on satellite operations, on such things as power and communication on the Earth's surface, and even some of the effects that this can have on the Earth's climate. Now, when you talk about weather, sometimes we talk about weather, but we can also talk about people's attitude about the weather. Oscar Wilde, for example, said conversation about the weather is the last refuge of the unimaginative. That may be sort of true of space weather as well, I don't know. The American humorist Ken Hubbard noted that don't knock the weather, 9/10 of the people couldn't start a conversation if it didn't change once in a while. That's probably also true. But a more formal definition of space weather is that it refers to the conditions in space that arise from the sun, from all the things that emerge from the sun that I'll talk about today that can disrupt power systems, satellites, aircraft, satellite operation, communications, and so forth. And so this has joined a host of other natural hazards that are giving some people probably hazard fatigue, just worrying about all the things that can happen to our modern technological society. I hope you can see this animation. I contend in this that the most important star in the universe is our sun, at least from our point of view as humans occupying a small planet around that sun. The sun, of course, is a fascinating object in its own right. The nuclear furnace, the fusion furnace at the center of the sun, releases energy, takes maybe 200,000 years to get out to the edge of the radiative zone. Then there's an outer part where there's much more upflow and downflow, convection. And this outer third is a region where there's more rapid rotation at the equator than there is at the pole of the sun. This leads to large scale kind of differential flow that leads to dynamo action, gives rise to strong magnetic fields. And the surface that we see, the photosphere, when we're looked at in more detail, is a constantly roiling surface with upflow and downflow. There are active magnetic regions called sunspots to vary over the sun's surface on an approximately 11-year period. And those sunspots give rise to strong magnetic disturbances, which can affect our life here on Earth and regions in space. There can be large expulsions of material from the surface of the sun, like this prominence that's seen here. We also see these bright patches that give rise to stronger magnetic field, but the overall magnetic structure of the sun is crucially important. If we block out the bright central part of the sun, then we see these blasts of material coming out that I will talk more about, that constitutes a real risk to human technology. And the bright patches we see here can also have strong interacting magnetic fields that give rise to powerful solar flares. And these solar flares can also cause disruptions, which I'll talk more about. So what we see with the sun, of course, then is a very important thing for our life, but also one that can cause significant damage to our systems and complications to our technical lives. This is a picture that's an assemblage of images taken at about 1-year intervals over the 11-year sunspot cycle. The part here is when the sun was at its more active phase, moving through the more quiet phase, which, by the way, we have just been in the last 2-3 years have been in the dead solar minimum time, so the minimum of sunspot activity. And then the sun reemerges and comes back to a more active state, and we're moving toward that. That will occur in about 2025 or so is the current estimate. Anyway, we've been living in a golden age of solar observations. This is just some lovely images taken from some of the satellites that are currently operating in space, showing some of the features in different wavelengths and so on. The sun is a fascinating object which we can study in exquisite detail from our perch here on Earth. If we look at one of the active regions on the sun, this is from back in October of 2003, the so-called Halloween storm period. We see that the sun was very active at that time, was popping off these large blasts of material. What you see as the snow in this picture is really hundreds, thousands, millions of solar energetic particles that are actually interacting with the CCD camera on board this SOHO spacecraft. It doesn't take much imagination to think about how a human eye or human brain being impacted by those kind of charged particles would be pretty well lit up by that. We take a look at one of the principal worries that we have about major space weather, and that's coronal mass ejections. And this region on the sun, a region on the sun, loses equilibrium, a large blast of material, perhaps as much as 10 billion tons of material moving out at 10 million kilometers an hour or so, can reach Earth in much less than a day. the magnetic fields are oriented right, this can open sort of the gate through magnetic reconnection to impart huge amounts of energy into the Earth's magnetic environment, the magnetosphere. The energy from that can flow down into the polar regions of the Earth and cause powerful disruptions, as we'll talk about. So coronal mass ejections are one of the big worries. Now, in the Earth's vicinity, there are hundreds, thousands, and there are many tens of thousands of planned spacecraft that are going to be operating. Just one region, the geostationary orbit at about 6.6 Earth radii from the Earth's center, has a lot of communication satellites and other operational spacecraft. This is a very old picture, but there are hundreds of billions of US dollars in space assets just in this one region alone. And of course, there are plans for SpaceX and others now to launch tens of thousands of new spacecraft. And so there are more assets in space all the time that are susceptible to the effects of the space environment. Space radiation, there are several different types that one is concerned about. Solar particle events, as I described, can impact spacecraft and cause large radiation effects on satellites or humans in space for that matter. The region around the Earth, the Van Allen radiation belts, are enhanced during these powerful solar storms, and they can develop significant effects both in space and on the ground. And then there's the persistent problem of galactic cosmic rays. These are very high energy particles that represent one of the long-term space radiation hazards for those who are traveling, say, to another planet like Mars or so. We published a lot of studies about the effects of the space environment, for example, high energy effects that can lead to single event upsets and other kind of micro interactions within sensitive electronics on board spacecraft. A more visible picture of this is sort of what I showed you before, the blinding effect. The picture before was at a stage before the solar energetic particle event started. Let's see if I can reverse this here. Go back, and just a few hours later, this is the same camera system, but now being heavily irradiated by the solar energetic particles. And so this blinding effect is a constant concern when there are powerful solar energetic particle events in process. Another effect is more due to high energy electrons, deep dielectric charging, where very energetic particles can enter through the skin of a spacecraft, bury themselves in dielectric material, and build up to very high levels. And this can lead to something almost like a small lightning discharge within sensitive electronics. And this is an example of the kind of disruption that can occur in a capacitor, a surface damage within electronics on board spacecraft. So these kinds of deep dielectric charging events at geostationary orbit have caused numerous failures or significant damage for spacecraft. For example, one that we studied quite extensively back in 1994 was a Canadian spacecraft that was put out of commission essentially permanently. So there are many new things to worry about with space weather because there are many new activities and it's an evolving landscape. There's increased precision global navigation satellite use. We'll talk more about that. The next generation air transportation systems, both in North America and around the world, are more heavily using the space sector. There's increased vulnerability of the power grid, and this is a concern on continental scales. Commercial satellite industry is much more active now and will just become more so. As you know, there are major plans for human missions to the moon and beyond, and the commercial space enterprise broadly is putting many new systems in space that are susceptible. And with the increased Arctic economic development, this is also a large concern. The global positioning system in the US or its counterparts, GLONASS in Russia or Galileo in Europe, are used in a huge variety of ways now. Back in 2003, when the Halloween storm occurred that I told you about, it was a relatively small business. By 2008, the forecast at that time, 2005 or so, was that this would be about a $20 billion business. And people poo-pooed the idea that it would reach anything of the scale of 750 billion US dollars as a business. But today, the utilization and the various things that rely on GPS and its counterparts is a 1.5 trillion US trillion dollar kind of a business. So it pervades our lives. It's used for positioning, of course, for surveying, for construction purposes, for oceanography, and a whole host of other things that were probably unimagined when the GPS system began in the late 80s or early 90s of the last century. One of the uses for GPS is to rely on this rather than ground stations. This, again, I apologize for the North America focus here, but the wide area augmentation system was intended to allow more efficient and effective flying of commercial aircraft over broad regions. And the idea was that one could reduce the distance between spacecraft and just have higher density and better navigation capability. This is an animation. In this, blue is good, red is bad. It's really showing the total electron content that's measured above the North American sector here, for example. This WASP system relies on there being relatively low density of the ionospheric electrons. In very short order, things went from a good state to a bad state back again in this Halloween storm period in 2003. And the whole system was brought to its knees and was out of commission for about 30 hours because of the strong effects of the high energy solar radiation that ionized and caused the ionospheric electrons to build up tremendously. So there's several ways that the global positioning system can be affected by space weather. There can be ionospheric range delays. This can cause loss of accurate positioning. There can be scintillations that can occur in the ionosphere due to significant ionospheric scattering. And there can be amplitude fading, which leads to degradation of the signals. And this, all of these things can make the GPS systems much less effective. Another worry for the airlines is really the fact that high energy X-rays from the sun can essentially cause significant disruption of high frequency and very high frequency radio communication. And in fact, the airlines rely quite heavily still on HF communication. So a flare goes off and essentially with no warning, 8 minutes after it occurs in the sun, the entire earthward, the entire sunward side of the Earth can have a radio blackout in at least some limited frequency range and can cause significant communication problems. More recently, over the last decade or so, there's been a tremendous increase in traffic of air flights from Asia over the North Pole to North America. This is an older figure now, but it really shows some of the main routes that United Airlines flies. And the requirement is that the aircraft need to remain in contact with their parent company throughout the flight. And at the highest latitudes, there can be significant problems using any other communication other than high frequency radio communication. During a time of large solar activity, again, go back to my favorite here, the Halloween storm period in 2003, this red area shown over the polar globe there is an area that was really blacked out by radio disturbances that were caused by very high energy solar protons funneling down along the magnetic field over the entire northern sector. And so this causes loss of the radio communication and basically causes the airlines to fly different routes or cancel routes entirely over the pole. Flying at lower latitudes takes more fuel, longer time, and is a real concern. Now, if we think about human space flight, not just flying an aircraft, but going out into space more, we have the International Space Station. And there too, high energy radiation from the sun can cause very significant problems, especially for extravehicular activity. And so it is part of NASA's plan that if there are strong solar particle events, that basically they have to abort human activities, move into safer regions on board the space station, and basically go into cocoon until it's safe to emerge. Space radiation hazards are a significant concern, not only near Earth, but even more so on the moon and going to Mars, for example, as is planned over the next decade or so. And I was privileged to chair for the National Academy of Sciences and Engineering Space Radiation Hazard Study. We issued this report back in 2004. So just looking at what the concerns are for space radiation and for human exploration associated with these programs. And this is a table from that study from the National Research Council, looking at some of the radiation risks. And you see here the production of cancers, degenerative tissue effects, damage to the central nervous system. What's listed as an acute risk as death, I guess that's a bad acute risk, but vomiting or nausea that can result very quickly from irradiation in space, having vomiting inside a spacesuit if you're out on the surface of the moon or so would be, of course, potentially deadly kind of effect. So space radiation remains one of the tall poles, as they say, for a long duration space flight. Now, to get more specifically to the title of the talk that I've given you all today, Societal and Economic Impacts, we realized back in the, a decade or more ago that there had been a lot of studies about the economic impacts of floods and earthquakes and hurricanes and things, but that there hadn't been a very systematic look at what the economic impacts of severe space weather really were. And so we did host under these aegis of the National Academies a workshop to look at that. We brought together experts from the various industries and issued a report, which has actually been one of the more successful reports for the National Academies. It's been translated into a number of different languages. And so I guess it's sort of a bestseller. But anyway, in this report, we looked at some of the interdependencies. I think this chart comes from our Department of Homeland Security, but it's a good chart to just make the point that there are some very cornerstone kind of technologies, electric power being one of the very prominent ones, that if you lose electric power, you quickly start to lose the ability for many kinds of transportation, for having emergency services, for communication, for pumping oil and gas, providing potable water, getting rid of waste, banking and finance can be severely affected, government services. And so losing electric power on a large scale for a long time is a very severe issue. This has been modeled by quite extensively, looking at particular storms, taking one of the largest storms on record from the early 1900s, 1920, but looking at today's power grid in North America. The sort of purplish and black lines here show the backbone, the extremely high voltage backbone of the electric power grid. And then modeled with that is what the effects would be on the transformers and stuff that are associated with that. And these red and green things just indicate where there would be extremely large flow of current in or out that could cause essentially disruption or failure of transformers on the power grid. And the idea of this is that there could be power loss over a very substantial portion, for example, 130 or 150 million people living in that circled area in the east coast of the United States. There have been a number of power outages and power grid failures, but the idea is that if such a thing occurred, if you burned out large transformers, you could lose power rapidly over broad sectors of the continent, and this would have extreme effects. Let's see if I can get this to move here. The largest event that, or a large event that people think about, the first large event that came to people's notice that affected severely the internet of the time, that was the telegraph system, was the Carrington event of 1859. Richard Carrington studied a large white light solar flare, the first one that had been observed. Just less than a day later, there were powerful disturbances on Earth. There were aurora associated with those solar disturbances that extended down into southern India and into Cuba. And so the extent of aurora and aurora kind of disturbances, excuse me, was substantial from this event. And the question would be, what would happen if we had such a powerful event today? How would a large solar event, coronal mass ejection, affect our modern technological society? And that, of course, is the $10 billion question. But the coronal mass ejections, as this Washington Post graphics indicate, the solar flares can have their effects, as I described. Coronal mass ejection can have their effect. All of these buffeting the Earth can produce a plethora of different kinds of effects, as I've talked to you about. The worrisome one is indeed the power grid. It's increasingly vulnerable, as many authorities have concluded, to the effects of very strong solar storms. These are low frequency events, blessedly, but they're high consequence. And estimates range from tens to hundreds of billions of dollars to perhaps, if the effects are long lasting enough, perhaps $1 trillion kind of losses. If you lose many, let's say dozens of these extremely high voltage transformers that are house sized and take months to replace, one could be looking at outages that would last for years, not days or weeks. And the effects of this could be quite devastating. Now people say, well, gee, 1859 was a long time ago, 1921 was a long time ago. We haven't had anything like that lately, so maybe we shouldn't worry so much about it. Well, actually, in this last solar maximum time, 2012, the sun developed a surprisingly powerful active region for such a quiet solar cycle. And this was in July of 2012. And a spacecraft, NASA spacecraft called Stereo A, was in the right position to see the sun, to see the disturbance, and actually see the active region that spewed out this blast of material. So there you see the coronal mass ejection, so-called halo event that's coming right toward the spacecraft. And this event was a real bell ringer as far as that goes. This is a difference picture, which really shows here the very nasty kind of active region, this magnetic field kind of signatures. So this was occurring on the far side of the sun. If this had occurred on the earthward side just a week earlier or so, the Earth would have been on a direct path for this. I should explain, just look at this side here. The Earth is here, here's the sun. Here's this blast of stuff coming out of the sun going toward the Stereo A. But if that event had occurred a week earlier, it would probably hit the Earth. And I've said in public and private that we'd probably still be picking up the pieces. We had the measurements from the Stereo spacecraft to look at what the magnetic field, what the solar wind speed was, the density, and so forth. And so we could actually take those measurements, run them through models, and actually predict what the disturbance on the Earth, the magnetic disturbance on the Earth would have been for such an event. And the largest, this is an index called the DST index. The details aren't terribly important. It's just the equatorial magnetic strength disturbance that was occurred with a magnetic storm. The largest storm that's been seen in sort of recorded history going back to the 1900s is really one that occurred in March of 1989. The modeling of the inputs that we have from the event that was seen by Stereo A was that this event would have been at least twice as large, probably several times as large as the largest storm that we experienced, which was March 1989 that caused the power outage in Hydro-Quebec that as sort of the model for bad effects on the power grid. This is another study that was done by another group beside ours, looking in more detail at the stereo data, and they too concluded that this would have been a huge storm had it really struck the Earth. This is a very slow animation. It's sort of a slow-mo picture of this, but it helps me give a little time and lets me point to some facts here, which is we're looking down on top of the sun. We're watching, this is a coronal mass ejection that occurred before the one that stereo was so worried about. It was a sort of a smaller and slower one. It sort of cleared out the entire inner part of the solar system. Stereo is at the same distance, by the way, as the Earth, 1 AU out, but was in a different location. But clearing out that inner part of the solar system allowed this next coronal mass ejection to move out at extremely high speed. And so this has become a new sort of paradigm now, that coronal mass ejections, one after another, can be particularly devastating. So let me point out that we don't have to have exceptionally large number of sunspots or peak sunspot activity in order to have the largest of these powerful solar storms, geomagnetic storms. The Carrington event occurred during a sunspot peak that was weaker than the sort of average. It's a black line here, 100. The 1921 storm that was modeled quite extensively, also extremely powerful, was a weaker than normal. I guess I haven't run this out to the 2012, but that was also a weaker than normal cycle. So weaker than normal or average sunspot peaks still can produce very powerful solar storms. What are we doing about this? What do we need to do about this? Well, we need to measure and make observations in a more systematic and operational sense. And so we've had some wonderful scientific missions, like I was principal investigator on an investigation on the Van Allen probes, or the radiation belt storm probes mission, 2 spacecraft that were flying through this Earth radiation region. Sort of our space weather picture here is the picture of the measurements looking down on top of the Earth. I don't know if you can see my pointer here, but looking down on top of the Earth, spacecraft moving in this elliptical orbit sort of measure and can let us get a complete picture of the radiation environment around here. And you can see on timescales of a day or so, you can have huge differences, changes in the high energy radiation. These are multiple megavolt electrons that can cause the deep dielectric charging. So having these kinds of observations in perpetuity 24/7 is really one of the goals that we have as space weather practitioners. We have a lot of satellites that are in orbit, moving around the Earth in various ways, but these are sort of catch as catch can, and we really need to have a much more systematic and long-term commitment to making observations in low Earth orbit, medium Earth orbit, and out to high Earth orbit. That's a crucial thing going forward. So let's see if I can move forward here. So we have studied this. We've made recommendations to the agencies like NASA. And I was privileged again to chair for the National Academy's what we call a decadal survey. This is an aggregation of scientists in the community getting together on a 10-year kind of cadence to make recommendations to the federal agencies in the US about what should be pursued, what needs to be pursued. And we've recommended very strongly that we need to have much more significant and orderly investment. So let me remind you what I've told you, and that is that that we need to address space weather. We need to look continuously and systematically at the 3-dimensional, the sun, to see what's coming at us. To understand that better, we need to know what's hitting or going to hit the Earth in its vicinity. We need to be especially cognizant of these coronal mass ejections and the powerful effects that they can have. But we need to also be aware of the high energy radiation from the sun. If that gets into the Earth's vicinity, it can produce the plethora of effects that I've talked about. the powerful currents flowing in the auroral region can couple into the long power lines and pipelines and can cause significant effects there. The kind of blackouts that occurred in Quebec in 1989 could very well occur for a storm coming up in this next solar maximum. The effects on the ionosphere, the high frequency radio communication, both ground to ground, as well as to airlines, and the transmission through the ionosphere and disruption that can occur there, the effects on such things as ATM and other financial actions, loss of GPS signals, can spell disaster for modern precision agriculture, navigation at sea, and all the other things I've talked to you about. Radiation effects on satellites. Now we're looking at constellations of hundreds or thousands or tens of thousands of spacecraft. Any one of those spacecraft could be significantly damaged due to space weather. And of course, the effects on humans, not only now for the space station, but going forward in a few years' time, we will probably have astronauts or other humans on the surface of the moon. So solving the space weather problem really means that we have to have these kinds of systematic observations. It also means that we have to have very capable and effective modeling, and together that these things can provide the improved forecasting that can give warnings not just of a few minutes, but hours or even days. So let me summarize here, leave some time for questions, but let me make the point that the challenges of space weather really affect all developed and in fact developing countries, and both civilian and military systems. This is an effect that knows no national boundaries and is really something that affects any system in space or near the Earth's surface. Work on space weather specification, as observations, modeling, and forecasting, we believe has great societal benefit. So I often say it is basic research, but with a high public purpose. Future space exploration, human exploration, most modern human endeavors, in fact, will require that we have much deeper understanding of the effects of and what causes these effects, deeper understanding of the sun, so that we can improve our forecasting and then transition that research toward operation. And the last thing I just want to dwell on a little bit is that you might say, some people say, well, this is like Chicken Little, the sky is falling. Geez, do we really need to worry so much about this? I would contend that it's not a question of if, but when there will be the kind of severe space weather effects that I've talked about here. But we want to be sure that we are not being unduly sensationalist about this, and we want to avoid this Chicken Little syndrome, and we want to have proper attention drawn to this by policymakers. And I would say that we have been making progress on this in the last decade and a half, and that space weather has now moved into the pantheon of natural hazards, along with earthquakes and hurricanes and other natural concerns, and that many of the things we need to do to deal with space weather are not so dissimilar from what we need to do for other natural hazards. And with that, I'd like to thank you and open up for questions.
Great, thank you for a very interesting talk. We have a few questions in the chat. So Franca, let me just find you, and I'll allow you to turn on your, so you should be able to unmute and turn on your camera.
Yes, I can. Can you hear me?
I can hear you, yes.
Okay, so I was wondering, you mentioned this analysis and this amount of money that would be lost in a solar event. I was wondering, was there also an analysis done about the possible loss of life what kind of order of magnitude that would be?
Yeah, it looked more at the let's say the economic disruption, and but quite honestly, there would be really life-threatening situations. The loss of power can spell disaster in a variety of ways, as we've seen, for example, with Superstorm Sandy in the United States. If you lose power, people can't make it to the hospital. There can be deaths that are associated with that. You may be asking more directly about radiation-induced deaths and things like that, and those were not so actively considered. There almost certainly could be fatalities for astronauts in space or on the surface of the moon. For example, going back a long, long time back into the Apollo era, there was one of the most powerful solar energetic particle storms ever in August of 1972. This occurred between Apollo 16 and Apollo 17, and it was concluded that if that had occurred at a time when the astronauts had actually been on the surface of the moon, that would have been a fatal dose of radiation there. So your question has many different layers. The disruption and loss of electricity and so on could produce deaths in a number of ways, but I don't think there was really an attempt by the insurance companies to put a price tag on that exactly. It was more the loss of economic activity and associated things that led to these hundreds of billions or trillions of dollars lost. So I hope that helps answer the question. I can tell a little story. We had an article that came out about space weather, and a woman in France read that and sent me an email saying that she thought this would be one of the worst things that could happen. And so she'd asked the emergency preparedness people in France what she should do if there was a forecast of a severe solar storm. And they said she should buy a large cake, eat it, and wait to die. And I thought that was a little rude as far as an answer from government officials, but I'd like to give more encouraging advice than that.
Okay, thank you. We have a question from Nuno, so I think it should be.
Yeah, I can talk. Thanks for the talk. It was very interesting. So you talked mostly about monitoring the space weather and the kinds of damages it could potentially cause. Do you keep tabs on material research that could combat that, or is the damage fundamentally impossible to fight?
No. You're asking a great question, and in fact, it's the preferred thing for any natural hazard, I guess, to engineer around it if possible. And so a lot of energy is being put into this in a variety of ways. And of course, in my own work, which is mostly about space exploration, spacecraft and spacecraft design, instrument design, we put a lot of energy, excuse me, into developing superior shielding to help protect instruments that are operating or spacecraft that are operating in space. And that's long been one of the approaches, is to just try to develop more robust electronics that's more immune to the effects of radiation, or to develop more capable shielding that's still affordable. And on the ground, there's a lot of effort that's going into trying to develop, let's say, techniques to protect the power grid so that it wouldn't suffer such severe consequences if there was a powerful coronal mass ejection related geomagnetic storm. One of the troubles with engineering around it is you may sort of cure one problem but increase the effects in another domain. It's sort of like the game whack-a-mole. You get one thing down and something else pops up. But you're absolutely right that the best thing that we could do, if we could afford it as a society, is to build systems that were entirely robust and completely immune to the effects of space weather. But the trends are actually in a different direction. I would say that many of these constellations of small spacecraft that are being put up now are just being minimally kind of shielded, minimally protected, with the idea that they simply can be replaced. And this is actually creating a new problem, which is space debris, where we're now seeing huge proliferation of spacecraft, many of which are no longer operable, and which are not going to come down for a long time. And so we're creating a different kind of sort of anthropogenic space weather effect, human-caused space weather effect, which if we start to have more collisions of spacecraft, we're going to create more space debris, and it may make certain regions of near-Earth space unusable. But I take your point. I think all the people working in these domains would love to be able to understand enough to be able to engineer around the space weather problem, rather than just being aware of it and hoping for the best.
Okay, thank you. Are there any other questions? Just wait. Yep, sure. Matteo has a question. Let me just find you.
Okay.
Yeah, you should be able to unmute and turn on your camera now.
Okay, here I am. Can you hear me?
I can hear you, yes.
Yeah, hi Dan. Thanks for the great talk. I'm now one of the students and one of the other speakers. I am the editor of Physics Magazine, so it's.
Oh, okay.
I was curious about this sort of crowding in space that you're mentioning. I'm looking at it from another perspective, how it's going to affect measurements of the cosmic microwave background. I didn't realize that there was another secondary consequence of that. So what do you think are the prospects? I see that SpaceX has filed for sending 30,000 new satellites. Is there at least going to be a part of this satellite? Are they going to contribute to measuring space weather and give us better information, or no, they're just...
Yeah, let me answer your first question, or your last question first, maybe. A friend of mine, a colleague of mine, one of the graybeards of space weather long ago, told me that every system in space is a space weather detector, whether it wants to be or not. And so every spacecraft that SpaceX sends up is going to be subjected to the space environment, is going to be measuring energetic particles, or going to be affected by it. So we're pretty big advocates of most of these systems having at least a simple radiation detector to help us piece together what the space environment really is doing. Now, with respect to the broader question, you've put your finger on something that I think is of absolutely crucial importance, and that is that we need better policy about how much stuff we send into space, where we send it, how long it stays there, and if it becomes inoperative, how you get rid of it so it's not clouding things up. And yeah, for astronomy, you start to put that many reflecting objects flying around in a shell around the Earth or so. It's going to be very detrimental. It's already been proven to be detrimental to observing. And when we start to add even more at different levels, as many companies now want to do, the effects can be very severe. And now people who are trying to launch, say, operational satellites into space now have to be much more vigilant and have to do much more careful planning of when they're going to shoot something to go up through or back down through these bands of very dense small spacecraft and things. And as I mentioned, if you have one or two collisions there, and you can start to have something like, I guess it was the movie Gravity or so, where things start to really cascade and you could have a real mess. And there was the Chinese anti-satellite thing that was tested a few years ago that created quite a a new population of space debris just from that one kind of destruction of one spacecraft. So I think this is one of the issues that really calls out for policy action. And it's not one country's problem, it's the world's problem, it's the spacefaring, it's human future that really is at stake here. And to ignore this or to simply let it go on is sort of insanity in my view. Yeah. And people say, if you find yourself in a hole, stop digging, and we're still digging. So.
And do you think the scientists have the sort of representation and voice that they need? Or I imagine it's a field where regulations are really, there's a vacuum there. But I've seen other fields like, the ozone layer problem where people were able to act and think. And but here, is it just a conflict between commercial businesses and scientists, and we're going to lose? Or
it is a conflict between these different forces, but I think that it behooves scientists, astronomers, and Earth scientists and space scientists to all speak with a loud voice about that we've, as you well know, have done a pretty good job of polluting the Earth's atmosphere. We shouldn't be polluting our space neighborhood as well, and so I think it's going to take the same kind of concerted effort. It's going to take the same kind of international cry for action, and the same kind of thing as for the ozone hole with CFCs and stuff, is to really get an orderly approach to this and make sure that that actions are taken that make this a manageable rather than a completely runaway kind of a problem.
Thank you very much.
Yeah, thanks for a good question.
Great, thank you. We just have one more follow-up from Nuno. So I think you should be able to unmute and turn on your camera if you want. And
so I do have a follow-up, and it's a bit on the topic you were talking about. So you talked that the space debris were one of the man-made problems created by this effect. Are there any other known or projected problems that will arise from human activity in exploring space?
Yeah, it's a great question. There are, in fact, some colleagues and I wrote a paper, I guess, that appeared in the journal Space Science Reviews. I can provide to Pedro that reference, but it was a whole article about anthropogenic space weather, human-caused space weather. One of the most, one of the ones that really is very alarming is if there were a nuclear explosion in space, as there was back in the early 1960s, this could really take out many of the operational satellites that we rely on. If I might just expound on that a little bit. Just before the nuclear test ban treaty, partial nuclear test ban treaty went into effect, the United States decided that it should explode a very large nuclear weapon above Johnston Island in the South Pacific. It loaded the magnetic field around the Earth with high energy electrons from the fission weapon. And it increased the radiation levels in the inner part of the magnetosphere by, our estimates would be something like 10 billion times or something like that. It caused the failure in rapid succession over 2 weeks of about 20 or so satellites. There weren't that many satellites in orbit around the Earth at that time, and many of them were killed by radiation dose effects there. So if that were to happen today, if there were to be a nuclear explosion in the right place at the right time, or the wrong place at the wrong time, maybe better said, that this could really take out a lot of the satellites on which humanity relies. So, given the previous question, I guess this is one way of taking care of the satellite problem, the debris problem I was talking about, except the debris would still be there. It would just be inoperative satellites. And so whether it is human effects by debris that I was talking about, or whether it's nuclear explosions that could knock out satellite communication satellites and other things like that, or a number of other things that we addressed in the Space Science Review article. Humans have been having effects on near Earth space for quite a while now, and could have a lot more. And it's really something that needs to be dealt with again in a strong policy way. Thanks for the question.
Thanks for the answer. I would be glad to read the article.
Okay, I'll get a link sent to Pedro about that.
Yeah, yeah, I can then forward it to Nuno. No problem about that.
Thanks a lot.
Any other questions? If not, I'd like to thank Professor Baker again for having accepted our invitation. I think it was a very interesting talk, very timely at a time where we might start to send more routinely people into space, and particularly also as scientists to see the policy side and policy making, and how as scientists and young researchers we might influence what happens in a few years' time. So thank you.
Well, thank you, and good luck to everyone, and thank you for the opportunity to talk to you. It's been a pleasure to be here today.
Thank you.
Thanks. Talk to you later.